Welcome to lecture 11. Let's look at how we will go about solving this theory of elasticity equations. But the first step is to really remember what the equations look like. We have this body of material, and this body of material has a traction load applied, T, has a body force, B, has an acceleration, A, and then we have boundary conditions are specified. And those boundary conditions are specified on portion S1, and I have this traction specified on portion S2, which is really the rest of this boundary from here to here out, from this point out to that point out. And we have the surface, which is made up of S1 and S2. And then we have the fact that S1 and S2 do not coincide, so it's null. And in addition to that, we called S1 to be the displacement boundary condition. And I've called the S2 to be the traction boundary condition, where loads are applied. And the body force are applied at every point in the body, so it's not a surface boundary condition. Their equilibrium equations told us, so we have three equilibrium equations. And the three equilibrium equations are sigma ij, comma j plus bi equals 0, or rho a I if we have acceleration. And that's in V, in the volume V. And the boundary conditions are either, you could have ui specified on S1, and then we have the traction sigma ij nj through Cauchy's relationship ti bar specified on surface 2. The compatibility equations, we also have the strain deflection relationships, and there are 6 of them, 6 strain deflection displacements. Relationships. And that relationship is going to be either the Green-Lagrange strain tensor, or we can look at the infinitesimal kind. Just keep it simple. I'll just say epsilon I j equals 1/2 ui comma j plus uj comma I in V. And then I have the conditions that we then, and I should have written this deflection specification here because it's related to the kinematics on the surface S1. And this is related to the equilibrium equation, so that's why I put it there. These deflections are related to the strain, so I'll keep it there. And the constitutive law, there are 6 components, 6 equations for constitutive law. And the constitutive law is written sigma ij, partial of W respect to epsilon ij, where W is the strain energy density function, and it could be a nonlinear function. It is elastic, so it's irreversible behavior, and it can be nonlinear. And we came up with an expression for linearity, and for linear conditions, we have sigma ij equals Cij epsilon KL. If we look at here and we count the number of unknowns, it's very simple to see that we have, and I'll do it in this corner, we have 15 equations, 3 plus 6, 9 plus 6, 15 equations. And the number of unknowns can be quickly looked at. So I have 6 components of stress 6 components of strain, and then 3 components of displacements. And that's 15 unknowns. 15 unknowns. And so 15 unknowns and 15 equations, that will take us to trying to solve these equations. And as you know, solving these equations will be quite complex. Here I have a more simpler manner to look at it in X, Y, and Z, so you can see them. So 3 equations, 6 strains, 6 stress strain deflections, 15 equations, 15 unknowns. And again, boundary conditions are specified, deflections are specified, traction loads are specified. And really what I'm trying to do is given a structure here, of some kind, so I have a structure, and I apply a load, what I want to calculate is where it's going to break and make the design stronger. So I have equilibrium equations, I have constitutive law, strain deflection relationships, nonlinear in this case, I included in higher order terms. And again, this could be even nonlinear, so derivative of W respect to epsilon ij, and that'll be fully nonlinear but reversible. And this is an error, so there's 6 strain deflection relationships, and you have to then solve all these equations together, and that can be very complex. And so the way we're going to approach solving this problem is to take a body of material and we're going to break it up in small elements. And then we're going to solve these equations in these small elements. And the elements we're going to choose could be either 1D, 2D, 3D, tetrahedron, solid elements, hexagonal elements, plates, shells, beams, trusses. We're trying to simplify, idealize a structure into something simpler that we can then solve these equations in. And so if I can solve the equations on one triangle, say, and I chose triangles, but it could be quadrilaterals, if I can solve it in one triangle, perhaps I can solve it for every single triangle and then connect the solution somehow. What is very powerful about this class and what is very powerful about calculus variations is I took a very complex partial differential equations, 15 equations, 15 unknowns, right here, 15 equations, 15 unknowns. And sorry about that. I have the 15 equations and 15 unknowns. And the main point I want to make is that you can solve it. You can solve these equations. So when I specify material properties, boundary conditions, and loads, I'll solve these equations in a way that is quite powerful, because I'll take these 15 equations and turn them into stiffness times deflections equals force. So I took a very complex partial differential equation, highly coupled, 15 equations, 15 unknowns, and turned them into just a matrix times deflection times equals a vector. And I can just solve for that deflection fairly straightforward. Once I do that, I can then plot. Once I can calculate for deflections, I plug it back in, get the strains. Once I get the strains, calculate the stress through the constitutive law, then I can plot it here to determine where the loads, where the stress will break. And here, if you have an aircraft, you're basically taking the loads, the boundary conditions, the material properties, the geometry, and putting this into a finite element model and then interpreting the results. And so to do this, we need to really understand the fundamentals of calculus variations, approximation theory, and how each of these theories for trusses, beams, plates, shells, solids have been derived. We already derived solids, the equation for solid, that's the most general case. We'll be going deeper into that as we move forward. Have a great rest of your day.